Hello viewers, I'm again here to take you on what we call the sum to infinity, the sum of GP to infinity. Okay, because infinity, you don't know the extent, you don't know where it stops. And as you can see in the first example I have here, I have 32, 16, 8, 4, dot, 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 showing that this continues to the last, to the point that we don't know. What we ask to add this thing to the point we don't know, that is to infinity. And let me remind you, you can only get the sum to infinity of a GP if the common ratio is less than 1, because it's going down. Okay? But if it is something that is increasing, it's impossible to get infinite, because the more you go, the more it continues to grow. So if you see that you get a number you can't count, a number you can't add. But for a GP that is decreasing, tending to 0, it's key that there will be a point you will go, and if possible, you can get 0. So that is why you can get the sum to infinity of a GP when the common ratio is less than 1. Now, I have to tell you the formula you use whenever you are asked to get the sum to infinity of a GP. Remember that the formula you use to get the sum of a GP when the common ratio is less than 1 is S. This is the formula you use. Okay. Now, let's assume that we are talking about sum to infinity. So we now have something like sum to infinity will now be A into 1 minus R power of infinity all over 1 minus r. That is what it is, because n is now the sum to infinity. Now, there is what I want you to know today. Whenever something is raised to a power of infinity and that value is less than 1, let's say half, or let's say 1 over 3, or 2 over 5, you see, as you are raising it to a power of numbers, let's say 3, the number will keep on tending to 0, because a decimal times a decimal will keep on giving you smaller values. So if you keep on raising it to power to up to infinity, where we get to a point where you will times it, the value will be almost 0. Therefore, whenever you have your r to be less than 1 and you are raising it to a power of infinity, this whole thing here will tend to 0. Therefore, you can now write that the sum to infinity of any geometric progression will be a into 1 minus 0 over 1 minus r. Then 1 minus 0 is 1. We are left with the fact that the sum to infinity of a GP is now a bracket 1 over 1 minus r. So the sum to infinity will now be a times 1 is a over 1 minus r. So this is the formula you always use whenever you are asked to get the sum to infinity of a geometric progression. So let us use this formula to solve the number one question. In the number one question, our a first term is 32. Our r common ratio is 16 over 32, which will give us 1 over 2. That is our common ratio we have. So we plug them in this formula. We have that the sum to infinity is now a, which is 32 over 1 minus our r is half, minus half. So the sum to infinity will now give me 32 over 1 minus half is still half. So this is now 32. I'll change division to times and turn the next fraction upside down. So the sum to infinity of this GP will give us 64. Okay, so the sum to infinity of this equation is 64. When you keep on adding it to the extent that you get to a point where you can't go further, you are getting 64 as a sum to infinity. So now I want to tell you the importance of this sum to infinity of a GP. It can be employed to change some recurring decimals that are repeating into a fraction. Is possible with the help of this sum to infinity of a GP, and that is what I'm going to show you now. Okay, for number 2, we are asked to change to fractions. We'll have 0.333 etc. This dot 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 shows that it's recurring. This can be seen as 0.3 is 3 over 10, plus the other 3 will be 3 over 100, plus the next 3 will be 3 over 1000 etc. That is how it continues, because 0.3 is 3 over 100, 0.33, this 3 is behaving as 100, that is over 100. The next 3 is over 1000. If you have another number over 10,000 etc, that is how it goes. So you can see that this has formed a sequence or a series, okay, where the first term a is now 3 over 10. As you can see, the first term 3 over 10. Now our common ratio will be second term divided by first term as usual. Second term is 3 over 100 divided by first term, which is 3 over 10. This will give us 3 over 100 times, I will change division to times, turn upside down, 10 over 3. This will cancel out, 0 will cancel 0. So we are left with the fact that our R is 1 over 10. So our common ratio is 1 over 10. And remember that because this thing is recurring, it will tend to infinity. Hence, we use that the sum, which will give us the required answer, will now be a over 1 minus r, the sum to infinity. Because it is recurring, we don't know where it will end. So we have that the sum to infinity will now be a first term. Our first term is 3 over 10, as you can see. So we have 3 over 10 over 1 minus r. Our r is 1 over 10. 1 over 10. So sum to infinity will give us 3 over 10 over 1 minus 1 over 10 is just 9 over 10. So finally, sum to infinity of this GP will be 3 over 10. I'll change division to times, turn upside down, 10 all over 9. Okay, 0 will cancel 0, 3 here is 1, 3 here is 3. So the sum to infinity is giving us 1 over 3. So you've now seen that I have converted this 0.33, which is recurring, into a fraction as 1 over 3. And when you take your calculator and divide 1 by 3, you will see it will keep on giving you a repeating 0.3333. This is one of the applications and the importance of the sum to infinity of a geometric progression. So let's take the last one. The last one here, we have 5.2525. So this is a whole number. So let us keep the 5 aside. Let us call this 5 plus 0.252525 etc. So let's keep this 5 aside and work with this after we add back the 5. That's the trick. Now, this is the same thing as 0. You see here, 2 digits are repeating, not 1 digit. Before, only 333 is repeating, but now 252525 is repeating. So the first 25 can be seen as 25 over 100 plus this 25 here should be 1, 2, 3, 4, should be 25 over 10,000. Okay, because before you get to the last digit, you count 1, 2, 3, 4. Now this one, before I get to the last digit, I will count 1, 2, 3, 4, 5, 6. So it will be 25 over, I'll add 6 zeros because getting to the 5 digits, I'm counting 6 places plus dot dot dot. Okay, now my first term, this can be reduced to their lowest terms. It's possible. 25 here is 1, 25 here is 4, 25 here is 1, 25 here is 400, 25 here is 1, 25 to 100 is 4. How many zeros are left? 4 zeros. 4 zeros. So this can be written as 1 over 4 plus 1 over 400 plus 1 over 40,000. Okay, plus bum bum bum. Now from here, my first term A is 1 over 4. My common ratio is something as saying second term divided by first term. So I have 1 over 400 divided by 1 over 4. Okay, so I will change division to times. I'll have R as 1 over 400 times 4 over 1. 4 here is 1, 4 here is 100. So common ratio is now 1 over 100. So I will now apply the formula for getting the sum of a GP to infinity. So S infinity will now be A over 1 minus R. So S infinity will give me A first term is 1 over 4, 1 over 4. Divided by 1 minus my R is now 1 over 100. So S infinity will now be 1 over 4 divided by 1 minus 1 over 100 will give us 99 over 100. This is the same thing as 1 over 4 times, I'll turn upside down, 100 over 99. 4 here is 1, 4 here is 25. So the S infinity will give us 25 over 99. This 25 over 99 is for 0.252525. But remember, we dropped 5, so we can add 5 to it. So I'll clean here. So remember, we dropped 5 in the beginning. So my S infinity, what I'm looking for will be 5 plus 25 over 99. If I like, I will call it 5-fold number 25 over 99. If I don't like, I will change this to improper fraction by saying 99 times 5, which will give me 495, 495. Okay, then plus 25, it will give me 520 all over 99. So either this or this is okay, and that is the application of sum of GP to infinity. If you've enjoyed what you've watched, kindly subscribe to my channel so that you don't miss anything. Thank you.